So now we're ready to prove this main theorem of the signed measure, the 2D decomposition theorem. Before we start, I just want to point out in the technical lemma we proved in last video, I actually should miss a condition that I should say this positive subset of this positive measure set E. It's the mu of this P has to be strictly positive. Okay, this is fairly clear from our construction. Our construction of this P is by taking away a bunch of negative measured subset of E, and then we get a positive, because mu of E is already positive, strictly positive. By taking away these negative subsets, we get something that's strictly positive. So now we're ready to prove this first theorem called the Hein decomposition theorem. So it basically says the following: if I have a signed measure on a measure space, then this measure space X can be decomposed as a positive part and a negative part, okay, where this P is a positive set and N is a negative set. And this decomposition is, well, it may not be unique, but unique up to set difference by null sets, okay? So if I have another such decomposition as P prime and N prime, then P and P prime and N prime, their set difference are null sets. All right, so let's prove this fact. So without loss of generality, let's just assume mu is never equals to positive infinity. Okay, so if mu takes positive infinity, let's just consider negative mu. All right, so let's consider the following. Let's consider the supremum, let's call it alpha, of all the mu of E where E is a positive set, okay? Recall positive not only means its measure is positive, but all subset of it also have non-negative measures. All right, because it's a supremum, there exists a sequence of Pn, let's call them Pn, they're positive sets. And this mu of Pn is going to converge to the supremum alpha. And we showed from last class the union of these Pn, the union of positive sets is again positive. So let's give it a name, let's call it P. So because everything is positive here, the mu of P is going to be greater than or equals to mu of Pn, because P is a disjoint union of Pn and P take away Pn, and everything is positive, okay? And now the right-hand side converges to alpha. That just shows the left-hand side is also, well, it's actually equals to alpha. And because mu never takes positive infinity, so this alpha is never, it's a finite number, basically. All right, so now I find a positive set P, and I just want to let N to be its complement, okay? So let N to be the complement P, and now let's claim that this N is negative. Okay, so if N is negative, then we already get a partition of this X as P union N. All right, to show it's negative, assume otherwise. What happens? Well, if it's not negative, it just means I can find a subset of N, let's call it A, where mu of A is strictly positive, okay? Well, because it's strictly positive by the lemma we just proved in the last video, so here A is just a measure, non-measure is strictly positive. It doesn't mean A is a positive set, okay? But by the lemma we proved, there exists a B subset of A, where B is a positive set, okay? And as I pointed out, we can assume this mu of B is also positive, okay? Strictly positive. Well, but now if I consider this B union P, okay, this is positive because it's a union of two positive sets. And this is a disjoint union because B is in the complement of P. So this is a disjoint union. So in particular, this mu of B union P is just going to be mu of B plus mu of P. So because mu of B is strictly positive, this is strictly greater than mu of P, which is, by our choice, is the maximum possible mu of a positive set. Okay, so now you have a bigger positive set. That's a contradiction. Okay, so this is a contradiction. All right, so now we prove that N is negative and we found a decomposition. And suppose I have another pair, which let's call them P prime and N prime. Okay, satisfies everything. Then what I have is that I want to show that P and the set difference, the P and P prime, their set difference has to be a null set, okay? So, well, that's fairly simple. So first of all, this, if I consider the P take away P prime, okay, so this is a subset of P. So it's very clear from the definition of a positive set that subset of a positive set is, again, positive. So this P take away P prime is going to be positive. And on the other hand, this P take away P prime is also a subset of N prime because it's contained everything that's not in P prime, okay? So because it's a subset of N prime, so subset of negative set is going to be negative, okay? And because you have something that's both positive and negative, so subset of this has to be non-negative and non-positive, so it's going to be a null set, okay? So this proves that this is a null set. And you do the similar for the other direction and also for n. Okay, so do similar proof for p prime take away p, and also the n take away n prime and n prime take away n. Okay, so everything, all of these four sets are null sets. Okay, so their set difference are all null sets. We're now ready to prove another very useful decomposition of the sign measure. It's called the Jordan decomposition. So first, let's give a definition. So suppose I have two sign measures, mu and nu, okay? So we call they are mutually singular if essentially just saying they're supported on disjoint set. So if I can find a partition of X as A union B, here A and B has to be disjoint, and one of them is a mu null set. You can think about it as saying mu is kind of the non-zero measures are subsets inside B. So the A part is going to be 0 for mu. And similarly, if B is going to be a nu null set, okay, so then we say these two measures are mutually singular. And this is denoted by this mu is orthogonal to nu. So the Jordan decomposition theorem basically telling us if I have a sign measure, then I can find a unique decomposition of the sign measure as a difference of two mutually singular positive measures. Okay, so here's the statement. I have any signed measure, I can find a unique pair of, here the measure is just a positive measure, mu plus and mu minus. They're mutually singular, and mu is just the difference of these two measures. You can think about this Jordan decomposition as dividing a measurable function as the positive part and the negative part. So the mu plus is like the positive part of your sign measure, and mu minus is the negative part. All right, so let's prove this fact. This is really a consequence of the Hahn decomposition. So let's apply the Hahn decomposition. What I can do is that I can decompose this X as a positive set and a negative set. So X is P union N, where P is the positive set and N is going to be the negative set. So now if I just restrict myself on P, I get a positive measure, and I restrict myself on N, I get a strictly negative measure. So I just take the negative to get a positive measure. Okay, so let's let mu plus of A to be equals to the mu of P intersect A, okay, the A part and the P part, and the mu minus of A is going to be the mu of A intersect the negative part, but this will give me something negative, so I need to minus that, okay? And it's just by the construction of these positive and negative measures, you can clearly see that the mu plus and mu minus are going to be mutually singular, okay? Because mu is going to be, it's only taking negative value on the negative set M, only taking positive value on the subsets of the positive sets P, okay? So they're clearly mutually singular. And just from the definition, mu is their difference, okay? So mu is mu plus minus mu minus. This is also fairly clear, okay? Because the mu of, let me just briefly say that the mu of A is just going to be equals to mu of P intersect A plus mu of the n intersect A. Okay, so you divide it up. The positive part give you the positive measure, negative part give you the negative measure. All right. So we have at least one such decomposition, and I need to show that this decomposition is unique. Okay, so suppose I have another way to decompose it as a, let's say mu is equal to, let's say, nu plus minus nu minus, where nu plus is mutually singular to nu minus, and I have that they are just mu plus and mu minus are just new measures. Okay, so because they're mutually singular, then I can find a partition of these x. Let's call it p prime and n prime equals to x. They're disjoint, so that this mu plus is kind of supported on the p prime part. In other words, the n prime is going to be mu plus null. Okay, so mu plus is going to be 0 on the n prime part, and also the p prime is going to be the nu minus null. Okay, and because of that, if you look at every subset of this, for example, every subset A of this p prime, the mu of this A by definition is the nu plus of A minus the nu minus of A. But because p prime is nu minus null, this is going to be equal to 0. So this is just nu plus of A, which is positive. So this essentially proves that p prime is a positive set. And you do the same, you show the n prime is going to be negative set. So now you have another way of writing X as a disjoint union of a positive and negative set. So the Hahn decomposition tells you the P and P prime, they may not be the same, but they are really close. Okay, so the set difference of P prime and N, P prime and P and N prime, they are both mu null sets. Okay, so based on that, if you consider mu plus of A, okay, that's just going to be equals to the mu of A intersect P prime. And because P prime and P just differ by a null set, so you can show that this is also equals to A intersect P, which is just mu plus of A by our construction. Okay, so in other words, this new decomposition, the nu plus is going to be equals to mu plus, and similarly, the nu minus is the mu minus. All right. All right, so now we finish this two decomposition theorem. So I just want to make the following definition. So let's define the absolute value of a sign measure to be the positive part, and you plus the negative part. Okay, so you do the sum of these two parts. Just like when you have a real value function, the absolute value of this function is the sum of the positive and negative part. And you can probably see that our definition of something that's called a mu null. So if A is going to be a mu null set, that's just essentially saying A is a null set under the absolute value of mu. Okay, so it's a mu absolute value null.